Hi everyone. So I will be getting into slope fields in a few minutes, but I thought we really needed to take a second look at a topic that we were introduced to in Chapter 5 and has still been really challenging for people, or some people. Over to. Okay, so here's our f function, little f. And we know that big F of x is defined as the integral from 0 to x of little f of t dt. So if I integrate this picture, I'll be getting big F values. Okay, and we ideally know what we're looking at in terms of big F. Really don't want to read the questions that come with this problem until I know what I'm looking at. And right now, what's getting in the way of me understanding what f is this integral. And so if I take the derivative of both sides, on the left side I have d big F dx, also known as big F prime. And over here, derivative undoes integral. This comes down to here, and we say that's f of x. All right, so this is a graph not only of little f, but it's also big F prime. All right, so with that in mind, let's look at some questions. Big F is negative on pi over 2 to 3 pi over 4. Okay, so let's see what we can make of that. Here's pi over 2, and here's 3 pi over 4. Okay, and it certainly looks like after pi over 2 and up to 3 pi over 4, this graph is negative, but this graph isn't big F. This graph is big F prime. So what can I do here to figure out if big F is negative on that integral? Well, I can think of a number of things. And the first thing I want to try is I want to find out what big F of pi over 2 is and what big F of 3 pi over 4 is. I see from my big F graph here that big F is negative from pi over 2 to 3 pi over 2. And that tells me that big F is decreasing on that whole integral. But just because I'm decreasing, it doesn't mean I'm decreasing down here. I could be decreasing here. I could be decreasing this way. So I don't know quite yet. I do need to gather some more information. I will see that big F prime is decreasing from 0 to pi, which means that big F double prime would be negative, and therefore big F would be concave down from 0 to pi because of all of this decreasingness. Right? But let's see about big F. So what's big F of pi over 2? Well, that's going to be the integral from 0 to pi over 2 of, this is cosine x dx. Imagine you'd be happier if I called that 1 and negative 1, so that you really would believe it was cosine. So that's going to be sine evaluated from 0 to pi over 2. Okay, sine of pi over 2 minus sine of 0 is 1. 1 minus 0 is 1. Okay, so I have a positive value here at pi over 2 on big F. Now, what about at 3 pi over 4? Well, that's again the integral from 0 to 3 pi over 4 cosine x dx. And that's going to be sine x from 0 to 3 pi over 4. Sine of 3 pi over 4 minus sine of 0. 3 pi over 4, the sine value is root 2 over 2 minus 0, and I get root 2 over 2. So on big F, at one end of this interval, I have a y value on big F of 1. And at 3 pi over 4, I have a y value of root 2 over 2. And that's going to be about 0.707. So what do I know here? Well, I had a certain y value, and because big F prime is negative from pi over 2 to 3 pi over 4, I know that big F is decreasing. And sure enough, big F went from a y value of 1 to a y value of 0.707. And so when you ask me, is big F negative on this interval? I say, no. Big F is decreasing on that interval, but big F is definitely positive on that interval. Okay, next question. Big F is decreasing on pi over 4 to pi over 2. Okay, so what do we make of that statement? Well, here's pi over 4, and here's pi over 2. Is big F decreasing? Well, if you think this is a graph of big F, you definitely think that big F is decreasing on that interval. But we know that the graph is not big F. Instead, we know that the graph is big F prime. So how do I know when a function is decreasing? Well, I know when its derivative is less than 0. This is a graph of that very derivative, and that very derivative has positive y values. And therefore, no, big F prime is in fact greater than 0 on that interval. Therefore, big F is increasing. Big F is increasing because the y values on big F prime are positive y values. That means that big F has positive slopes from pi over 4 to pi over 2. So this is not a true statement either. Okay, and then finally, big F is concave up at pi over 2. All right, well, let's think about this. At pi over 2, that's this place here. Well, I see that big F prime is decreasing, 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 decreasing. That means that the slopes on big F prime from 0 to pi, the slopes are always negative on big F prime. If the slopes of big F prime are negative, slopes of big F prime are less than 0, that's the same as saying big F double prime is less than 0. And what do we know about that? Well, if big F double prime is less than 0, we know that big F is concave down. So big F is going to be concave down from 0 to pi, which includes pi over 2. So this was also false. Yeah, so we got to get you to that comfortable place. And hiding from questions like that, not a recipe for success. So please ask more questions. Okay, now slope fields. In the last couple of days or videos, we have explored the idea of solving differential equations so that we could have an antiderivative. And that process of using separation of variables and using differentials was pretty powerful. We could do a lot of problems like that. And so when we combine that with all the antiderivatives we're supposed to know, because we know how to take derivatives of so many different things, things are pretty fabulous. Well, what's going to happen is we're going to get stuff that we can't actually find the antiderivative for. But we'd still like to recognize the antiderivative. We'd still like to be able to have some ideas or thoughts about an antiderivative. Now, I'm going to start this process with functions that we really don't need a slope field for, just so you have a sense of comfort with what slope field means, does, how we use it, how we make one. So here goes with a gentle function that I don't actually need a slope field for. Let's say we've got this, okay? And I want to make a slope field. Okay. So AP will pre-print a little dot diagram like this for you to fill in the test booklet. It almost never has this many pips on it. But I figure for our first, we should embrace the process. So these are x values, these are y values, and what I'm going to do, because this function only has x's, I'm going to plug some numbers here, and that when I plug a number in here, for example, x equals 0, that's at all these places. If I plug in a 0 here, I get 2 times 0, or 0. What that means is dy dx, the slope on y at 0 will be 0. So there we go. 0 slope, 0 slope, 0 slope, 0 slope, 0 slope. What if I plug in a 1 there? Well, 1 times 2 is 2, which means the function y has a slope of 2 at every place where x is equal to 1. So slope of 2, 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 slope of 2. And if I go out to x equals 2, well, 2 times 2 is 4, so dy dx, the slope on y is equal to 4. Now, 4 is steeper than 2. And really, we're just looking for a comparative here. I just want slopes to be steeper here than they are here. Okay? What happens if I plug in a negative 1? I get negative 2. And what happens if I plug in negative 2? I have negative 4. Okay, so there's a slope field. Now, remember, if we go and integrate here, actually, I'm going to do that separation of variables first. We'll get that y equals x squared plus c. Okay, this is what y is. It's some sort of up-pointing parabola, and until we get an initial condition, I don't know, I've got an infinite number of them. Now, what I'd like you to be able to do is look at this picture and see that infinite number of parabolas. So maybe something like this, maybe something like this, maybe something like this. We've got an infinite number of parabolas here. So in a situation where I can't algebraically solve a differential equation, which was not the case here, but when we get to those problems where I can't solve the differential equation and come up with an antiderivative, what I can do is just take that dy dx equals and make a slope field and recognize the infinite number of antiderivatives presented here for me. This is a bunch of nested up-pointing parabolas. In fact, we could be even given an initial condition such that y of 0 equals 2. So when we see that initial condition combined with make a slope field, what they want us to do is draw the specific parabola that passes through that ordered pair. So 0, 2 is here, and this is my y function. Okay? They're not asking me to come up with an equation for that in this problem. They just want me to be able to say, I can see in this pattern of slope marks that I'm going to have a bunch of nested parabolas. Now, again, what was this slope field? It's a field of slopes, not on this function, but on the antiderivative. We're using the derivative to help make a map of slopes at points on the original function. And that's why we're talking about y here. I'm not seeing an infinite number of dy dx graphs. No, no, no. I'm seeing an infinite number of the antiderivative y graphs stacked here. Okay, so let's, why don't you try this next one? Again, we're not interested in solving the differential equation. We just want to use this derivative to help us build a slope field. So, slope field. The problem with slope field is, to get a good sense of what's going on, you need a bunch of dots. And sadly, though, we are an impatient people. What do you mean I have to make all these dots? And this might not be enough. I might want some more. Generally speaking, this is about the size that they put on the AP exam. Sometimes they chop a couple of points out, but they try to be humane. All right, so please make your slope field. Do not solve the differential equation. If you have something that says x to the third over 3 when you're done, you didn't follow the directions. You just need to make the slope field here. Okay, so why don't you pause the video and give it a go. Come back when you're done. Okay, so let's start. If I plug x equals 0 in, I get 0 minus 0 is 0. So every place x is equal to 0, that's on the y-axis, the slope will be 0. Okay, doink, 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 doink. Now, what about if I plug in a 1? Well, isn't that interesting? 1 minus 1 is going to be 0. And so I get another 0 slope here. And if I plug in a 2, 4 minus 2 is 2. So I draw little segments that look like a slope of 2. Slope of 2. And over here in negative land, if I plug in a negative 1, that's going to be 1 minus a minus 1 is plus 1. So 1 plus 1 is 2. So I've got a positive 2 slope again. And if I plug in a negative 2, I'm going to have positive 4 minus a minus 2 is plus 2. So 4 plus 2 is 6. Very steep slope over here. All right. Now, do you see it? Well, I know I don't want you to find it, but I kind of want you to think about, like, the antiderivative here is x to the third over 3 minus x squared over 2 plus c. And so I should be seeing something that's cubic. But I also notice that these are zeros. dy dx is equal to 0 at these places. If I make a y prime sign chart and put on 0 and 1, what's happening in between those? We found out that we would have a 0 slope on y at these places, and I see that here. But in between those two numbers, like at 1/2, what's happening? Well, 1/2 squared is 1/4 minus 1/2, and guess what? That's negative 1/4. So in between these two values, at 0 and at 1, I get a little negative slope going on. And so while it might have looked like we had this long flat shelf, no, that's not really what we had. In fact, what we had was this. This is happening at x equals 0, and this is happening at x equals 1. And in between those two horizontal slopes, if we check, like at x equals 1/2, we see a negative value on dy dx, which means our original function is decreasing. So this is the kind of thing that I'm supposed to be seeing in this picture. But it could well be that because I wanted a fairly small slope field, and it still felt like it was big, I may not be able to see that I'm supposed to do something like that. Okay? But that's what my slope field should look like, an infinite number of these cubic polynomials stacked on top of each other. And again, if they give us the initial condition, y of 1 equals 2, well, at 1, I want a y value of 2, and so mine is going to be this one. This will be our particular solution. Our particular solution would look like that. Like this. All right, and so far the slope fields we looked at, all we had to do was plug in an x. Well, what about this situation? dy dx equals x over negative y. So when I go to make a slope field here, let's see what happens. Okay. And now it looks like I'm plugging in ordered pairs. I mean, I can get a little, like a bunch of dots with the same slope. So if I plug in y equals 0, anytime y equals 0, doesn't matter what the x value is. If I plug in y equals 0, I get an undefined or vertical slope. Every place y is equal to 0. As opposed to if I plug in x equal to 0, if x is equal to 0, that's along here, I have a slope, or dy dx equals 0. Now, notice this troublesome point where I have both a vertical slope and a horizontal slope. Well, that's because I'm doing 0 over 0, and that's an indeterminate form. And so I'm actually going to leave that one blank right now. All right, so what about here at 1, 1? 1, 1, I get a slope of negative 1. What happens if I come over here, negative 1, negative 1, and negative 1, and negative 1? Well, I'm going to have negative 1 on top and minus a minus or plus 1 on the bottom, and so I still get a slope of negative 1. In fact, if I plug in 2, 2, I still get a slope of negative 1. And if I plug in negative 2, I still get that same slope of negative 1. And so that was kind of nice to go along the diagonal and have the same slope. I wonder if it works along this diagonal. What if we plug in 1, negative 1? 1, negative 1. Minus times minus is plus, and so I end up with 1 over 1, or positive 1. So I have a positive 1 slope there. I'll end up with a positive 1 slope there, as well here, and here. And if you're wondering how, remember, you could always take that ordered pair, negative 2, positive 2, and plug in. So negative 2 over minus positive 2. Negative divided by negative is, in fact, positive, and 2 over 2 is 1. And so, yeah, I do have that slope of 1 there. I do need to find these extra, or these other points that aren't along the main diagonals. How about this one over here at 2, 1? 2 over negative 1 means a slope of negative 2. Here at 1, 2, 1 over negative 2 is a slope of negative 1/2. If I come over here to negative 1, positive 2, negative 1 over positive 2, I have negative over negative, which is positive 1/2. And then here at negative 2, positive 1, well, negative 2, positive 1, I'm going to have negative 2 over negative 2, which is positive. Oh, I thought I did that one. Sorry, the bottom was supposed to be 1. There we go. Slope of positive 2. And down here, my slope will look like that, and like that, like this, and like this. Okay, so I need to fill in all those, and I need to see something here. What is it that I'm seeing here? I'm seeing a bunch of concentric circles here. I know from our work 2 videos ago, maybe even yesterday, the last video, that this differential equation solves to be a circle equation. And that's what I've got here. It's a little more work to have x's and y's to plug in, but I can certainly graph those pairs. How about this last one? How about dy dx equals 2y? Okay, dy dx equals 2y, and I've got a little slope field here. Boink, boink, boink. All right. There we go. And here, there's no x's to plug in, just y values. So when y equals 0, dy dx is 0. So 0, 0, 0, 0, 0. If y equals 1, dy dx is 1 times 2, or 2. If I plug in y equals 2, then I'm drawing little slopey segments of positive 4 slopes. Now, what about these negative values? Well, if I plug in a negative 1, I get a slope of negative 2. And if I plug in a negative 2, I have a slope of negative 4. So, do you see the infinite number of antiderivatives? Yeah, I do. So, remember what we'd be looking at here, okay? We solved this differential equation in a previous video. We said that dy over y equals 2dx, and we integrated. That gave us ln of y equals 2x plus c. We exponentiated. We had absolute y equals e to the 2x plus c. We turn that into e to the c times e to the 2x. To get rid of the absolute values, we shoved a plus or minus there. And then we said, okay, let's have plus and minus e to the c be something innocuous like b. And so we ended up with b times e to the 2x. And this is our constant. Now, let's think about what happens here. If our initial condition has a positive here, well, that's going to be a positive number. And if I have a negative, that's going to be negative. So this b value here is the thing that decides whether my graph looks like this or whether my graph looks like this. And so here I have exponential growth, and here I have reflected across the x-axis exponential growth. So, yeah, there's my slope field telling me you're going to have an exponential thing. Look, there it is. There's the exponential thing. I've got an infinite number of exponential growth curves and an infinite number of their reflections. So without having to go through this process, I can, by looking at the slope field for this, I can have a sense of what the antiderivative would look like. All right. Now, had we been together in the classroom, I would have infected your calculators with a program called Slope Field. You might want to, get this program into your calculator. I believe you can do it with a patch cable to your computer. But typing in the programs, yeah, it only takes like 15 minutes, and I'm sure there's a YouTube video to watch it. You won't need it. It's certainly not required. Just like all sums or RAM are programs that you can put on your calculator that do LRAM, RRAM, MRAM, as well as trapezoid and Simpson's rule for in the case of all sums. They'll compute those approximations, and you can even tell them how many subintervals you want, like whether I want 4 or 8 or 1,000. And so those are very useful programs, but again, College Board is not expecting you to have those, though they do help make things clearer with less suffering. And what do I mean by that? Well, when I look at dy dx equals x plus y, this is a situation where I don't know how to solve that differential equation. If I had x times y is dy dx, sure, no problem. I can divide both sides by y, multiply both sides by dx. 1 over y dy equals x dx. and I'm ready to integrate. They were attached with multiplication. But these are attached with addition. And because of that, I can multiply both sides by dx. But this needs to go over there, and I don't have a way to do that. Yeah, my algebra fails me here. And so really, the only thing I have handy for saying anything about the antiderivative of this would be a slope field. So let's make a little slope field and see if we can do something with it. Okay, actually I do want to quickly check my calculator. Yep, don't have the slope field program in this one. All right, so when x equals 0 and y equals 0, then dy dx is 0. When x equals 0 and I plug in any other y number, that y number becomes the slope at that ordered pair. So for example, at the point 0, 1, dy dx is going to be 1. At the point 0, 2, dy dx is going to be 2. At the point 0, negative 1, no, dy dx is negative 1. And at the point 0, negative 2, dy dx is negative 2. Well, what happens if I come over here and make x equal to 1? So 1 plus some number. 1 plus 0 makes 1. Same slope as over here. 1, 1 is a slope of 2. Oh, look at that. These slopes are the same, and these slopes are the same. What about 2, negative 1? What if we check 2, negative 1? So I'm plugging in a 2 for x and negative 1 there, and 2 plus negative 1 is a 1. Well, that's nice. I can go up the diagonal. This was a slope of 2. This was a slope of 2. X equals 2, y equals 0. This is a slope of 2. Okay. Here, will these all be slopes of 3? No, let's find out. This is over 2 and up 1. Sure enough, even steeper slope of 3. This is the point 1, 2. 1 plus 2 is also a slope of 3. Okay. Now, what happens down here? 1, negative 1. Oh, 1 plus negative 1 is 0. And 2 plus negative 2 is 0. And negative 1 plus 1 is 0. Look at that. 2, negative 2 is that one, sorry. 1, negative 2. 1, negative 2 is a slope of negative 1, just like here. This is a slope of negative 2. This is a slope of negative 3, and so on. And so, wow, what kind of function is this? Well, let's take a look. If we had the solution must pass through the ordered pair 1, 0, then our graph would look like that. Sort of slant asymptote here, and then dipping down and coming up kind of affair. Let's go a little deeper there. Okay, so that could be for that point, but if we had something like we need to pass through negative 2, 0. So we're passing through here. Mine's going to look like that. So it's a pretty interesting antiderivative, depending on what we end up for our C value. If we could solve this, would generate either something that looked like that. You can see a bunch of them here. Go up, there we go, and go up. It's almost as though we're headed towards some sort of verticalness thing, but I don't have one of those for sure. Or things that, are ever decreasing. It's just a really interesting space, this space of slope fields. So when I need a slope field, like dy dx, equals x plus y, which I can't solve and I don't recognize it as someone's derivative, slope field is the only way. So embrace the slope field. Love on the slope field. The slope field loves you. Okay? All right, well, that's our video for today. I hope it was helpful, and I look forward to seeing you in our next video.